This is an old slide, and it's back to before we had any luck. I was always concerned with steppiness in synthesis. I don't have much patience, and more than 3 steps, 4 steps. If I can get a natural product that's sexy and complicated, as long as I can get kilos of it, I'm happy with it. I don't care where it comes from. I just want Mother Nature to provide it, from petrochemicals or coal tar, and do a few steps. That's my idea of chemistry that can be used. But first you have to get function out of it, so there's not much evidence for this approach yet, so doing what I hope it can do. So click chemistry was just a few good reactions. It was like the Monish reaction, the Diels-Alder type reaction, the inverse Diels-Alder, the Michael reaction. Everybody likes the Michael reaction. And there aren't many that really work, really easily without making a lot of waste. And so you pick the best ones, and then you say, what can I put together like nature does? She only uses probably 30 building blocks in the main machinery. The sugars get really crazy, and then, but there's only 35, I think, or 38 that you can count in the main primary metabolism. When it comes to secondary metabolism, the little guys go crazy because they don't have any knives or guns or anything. All they've got is they got messages from the outside. There's somebody out there, and then they have to answer them with stuff. They do big job. Half their genome is in that biosynthesis of palytoxin. Okay, just to get your attention, this new click reaction, which is really a good reaction, it had no chance of being found by any rational way. And so why did we do it, and where did we get it? How did we get Vicane, for one thing? Well, what happened was, this is a later result, because we found strange things about the Vicane and what makes it react. It reacts, I tried yesterday, it reacts only at the interface with oil and water. And it's its Achilles heel. Otherwise, it's up there 20 or 30 years, and they just let it out. My house was fumigated when I was in China, and I was really unhappy because I wanted to catch some of the stuff, with liquid nitrogen and get not that I would have gotten liquid oxygen, but it just goes off. They don't ever save it. It reacts great with many things at the interface. That's the thing we discovered that wasn't known. And so we didn't even know if it would work at all because it was so unreactive. It boils at 55 degrees. It's like propane in the tank. It's not caustic, totally you just shake it. It's 4.2 times heavier than liquid propane, that's all. And it doesn't do anything. You just let it out. You can't smell it. So maybe a quarter of this room full of it for the time we're talking here wouldn't hurt anybody probably, but it hurts insects more. They're more penetrable. Their skeleton is easier to get through. But so we just bubble it, put a balloon on a flask, and stir vancomycin hydrochloride. That's the kind we take. It's a hydrochloride switterion. So you've got 2 amines. This one's amino acid intersalt, and then you just put the SO2 over with 4 equivalents of a tertiary amine, DCM, and you need the water. Without the water, this gets really messy. The water really makes things red properly, so that all that reacts are the phenols, and then it crashes out. It took a long time to convince Larissa Kresnova to try this, because it is like a peptide and it's ugly, but it happens with a lot of natural products that it has a taste for phenols. What can I say? It really likes phenols. He likes phenols, and this thing is not a normal phenol. It's a biphenyl biaryl. So this one cyclizes, and this one is a fluorosulfate. Well, we didn't know there were hardly any fluorosulfates in the literature. And there were cyclic sulfates way back to the man who's residence professor, Emil Kaiser did a lot of nice things with them. Now, if you take that a ducted material, the trisulfate, and this doesn't look like it's written properly. It doesn't have the charges showing, and I think, yeah. But you can see, this has an acetylene here, which was from an old project where we'd made about 50 grams of dimers and trimers of vancomycin trying to find something potent about 20 years ago, but never did anything. So we had the label here, and went back and made that, and then you put it into the proteome of E. coli or gram-positive, and well, if you boil the proteome so that you don't have any active proteins, they're all denatured, or you add SDS and denature it, you don't get any reactions. That's the thing about these sulfur compounds. They tend not to react unless the protein is alive. So it's sort of like, if you're alive, the protein, and Professor Warshall might have some thoughts about this, but it comes to my mind that we got some really hard ones, like the fluorosulfates. They will definitely not react with anything that's dead in organism juices, but they will react with some things really fast. And it's got to be an electric field of some kind, because there's nothing that's there except those flapping around phases of the oil and water of the protein that could be imagined to be different from what you have when you grind it up, and it's all still the same functional groups, right? So this thing was pretty good. It got more or less one protein. The guys who do this work, I shouldn't maybe show these slides, but it's like we haven't published it. I think we know what the protein is. That's the good thing about this. There's still antibiotics too, although this doesn't enter E. coli, so it doesn't kill E. coli. But if you make a proteome, of course it reacts to something in there because they're not protected anymore, and it's probably doing the cell wall machinery or something, or wherever vancomycin goes. I don't know. This is our sort of U.S. ego version of the planet, and I like the other version. There's one picture of Earth that's perfect, Bengt, right? Happy birthday for your sailing, happy birthday for being a great guy, and sending us all these things and making us jealous. But the Pacific Ocean is what Earth is. And did you ever, I don't know why, I lived underwater as a kid. I was really nuts about this estuary, Manasquan, New Jersey, and I don't understand why we came out of the water. I got pneumonia 12 times already. It's a weak interface, really, don't you think so? Okay. But here's it's a green. It's green, yeah. Well, the planet's not. It's much brown as it has green. But over here, this view is really awesome. It's all blue. And before the life came along, there wasn't any oxidized. It wasn't enough silica to melt when the trips under to come up as the plutons of granite. Silica's like cotton candy, density 2.6. It floats on the mantle, so that's why we have so much land and people and trees. That's in the way, really. The organisms that run the planet are not interested in having blockage on their viral transmission of photosystem 2. That's the only thing that matters on this planet. If that doesn't stay running on the surface waters, we're dead. So eventually. Okay, the sulfate. Now, what I want to talk about, you guys are in biology, most of you, and phosphorus is everything and everywhere. It's the energy source. It's it meters out little bursts of energy and pushes the world along for us. Then comes the connectivity for even Albert's favorite molecule, B12, has one phosphate connection and diester, and then other cofactors have 2 or 3 or 4 sometimes, and eventually you just break into the sugar patterns of ribonucleotides and DNA. So what I found was, if you look at this, I've always wanted to have why I want to get fluorine in our life was, I said, please try it. 30 years now, people have not been able to make sulfonyl fluorides. I really wanted like the sulfuryl dichloride, because I wanted to make ligands for osmium way back when. And it really gets me mad when that thing's chlorine. SO2Cl2 is really close to chlorine. Everything gets oxidized. So I kept hoping somebody would make and I can read German, so I knew the Germans had done this. But I didn't interfere with them. None of them succeeded. You wouldn't believe how many postdocs, graduate students I asked to make a sulfonyl fluoride. Just an aromatic one, like phenyl or toluene. They never came back with one. And this was just a funny thing. And I knew they would be very different, but little did I know how different they would be. So what I found was, and this is known in biology, of course, this is in the signaling for inflammation areas, the heparins and the blood thinners, and these are naturally put on to sugars in life signaling, and they, I guess, also tyrosine once in a while, but they're hard as hell to get off, and they have never been doubled up to make a sulfate, a neutral. Most of us think of explosions. We think dimethyl sulfate. That's really bad stuff. I mean, it's volatile. It alkylates everything it sees. So that's our experience of sulfates, esters, more or less. And if you look in the books, you don't find any diaryl sulfates. You find 5, how much is it? You find tons and tons per year of the phosphate, triphenyl phosphate, because that's used as a fire retardant. You can't buy a single sulfate, diaryl sulfate. And so we got a wrong idea about sulfate. If it was in the DNA connection, like Tom Brown and I talked about, because he could do that. I think it could be read through. It'll be stable. It's not going to break up. Yeah, it's harder to hydrolyze aliphatic sulfate, even though it's neutral, than it is an aromatic one. So once you have the aliphatic bonds in the sulfur, the two oxos, and then you have the inductive death out there to the SN2 on the carbon, you've got a compound that can be almost a solvent sometimes. We've had experiences where it didn't do anything with even azide. So we're thinking sulfate world is much bigger than people thought. And what's nice about it, you'll see the union is almost 100% yield, and it doesn't hydrolyze, no bacterium or anything we've had. If you want to volunteer to hydrolyze some, please, I'll send them. We haven't found anything that can hydrolyze it, even though it's neutral. And it's a diaryl. It should be easier. But Tony Kirby at Cambridge, whom I really admire as a physical organic chemist, he's done early work on showing if you put neighboring groups in next to the phosphate on the ortho position, you can get much faster hydrolysis. But the thing you'll see later, if I get there, is I showed it up front because I think it's really important I was talking to Andy McCammon because before we collaborated on calculating what triazoles would look like on either side. And the triazoles are okay, and they're good. They'll be good compounds, but if you get too many of them in a molecule, it gets clunky. Amides are clunky too, but it doesn't really look like a very druggable thing for a multiple connection idea. Whereas the sulfates are almost invisible. Look at this thin layer. This is 25% ethyl acetate hexane. Farnesol runs to there. Cholesterol runs to about there. I always use them. I tell them I want to see this because that's the world I grew up in. And that's the solvent system that moves things in moderate polarity. Look at the most polar compound. It's the sulfone. And here's a phenyl direct to sulfur fluoride. It's about the same as the chloride. I don't know, there's some impurity in one of these things. But the chloride runs very nonpolar too. Here's the phenyl fluorosulfate, much harder to hydrolyze. Also, the least polar of the bunch here, benzophenone here, these all cross the blood-brain barrier. We found that out accidentally a couple of times in the lab. That's an interesting story. It would have been a great drug. It would be a great drug still in the 60s up in the Haight-Ashbury because you get the wildest streams and things. Anyway, this is the baby. That's the one. So there it sits, and it rotates like crazy. You know, there's no barrier. There's hardly any X-ray. There's an X-ray of one of them, and it has two conformers about equal in the crystal structure. It doesn't give a damn which conformer it's in. There's no conjugation in sulfur, and there's none in phosphorus either. And people don't really face that fact. The Germans know this. A lot of good theory people in Germany, they just laugh at us because we still draw double bonds between. There are no pi bonds in sulfur or phosphorus. I'm saying a loud thing for a lot of people like calculators out there, like Michael and Ari. I don't know if I'm wrong, but I say these things because I want to get feedback, okay? I really would love to have somebody care about the bonding of the second row of the main group. It's a pretty important group. I mean, and you know, there's this guy was a genius, Glemser. He came out of the war, immediately got a group around him, and he did some amazing chemistry. There's this thing, thiazyl trifluoride. Thiazyl trifluoride has a little triangle of fluorides, and then here it has one nitrogen. That thing is very short, and people who believe in pi bonds, and some are really smart, they make xenon complexes, a man in Canada, but he writes these things just like pi bonds, and he describes it through the theory. Well, this is a mistake that Lewis was right and Pauling was wrong here, but Pauling was right about a lot of things. So it's heavy duty stuff. Maybe we can get some purchase on this thing because I think it's important for the mechanisms of the phosphorus. You like phosphorus too, right? Or mostly like tire. But I don't think people have any right to. There are no pi bonds. How do you do an attack like you do in a carbonyl? Forget it. That's why they're so funny. And this little thing, you put a dimethylamine into one of those fluoride positions. The Germans X-rayed the parent, minus 95 degrees. There's no picnic of that triazole, and it's very stable, more than Vicane. And the triple bond, so-called triple bond, doesn't move an inch, and it doesn't move at all. What kind of a bond is that? I mean, how can you? If you had cyanogen fluoride and put dimethylamine in, woof. I mean, this is, and then also you got the fact that if you have a nitrogen double bond to so an amide, the thing's freewheeling. This is like Lerner's thing about proving enzymes are jumping all around with Nicky's experiment. You know, this stuff was so obvious to Lerner and Nicky, but they never got it published because it was insane. Well, it's the same thing with the sulfur. You don't need too much evidence to say, hey, this thing, you got to forget about it. The d orbitals are just way too high. All they do, according to the guys who calculate in Germany, they polarize the antibonding orbitals nicely to these things. And you got these charges that are like triple bond, 2 pi's that are negative, and then there's the back bonding ones which are right. I mean, the antibonding sulfur orbitals. And they're happy to keep spinning. They're still doing the same thing, right? But they don't want to talk about pi bonds. And that means it's hard as hell to break into those things from the outside. There's no openings. And then you go to the reverse phase. I had trouble getting this lecture because I got a bad cold, and so I was fighting till the end. I missed Jean-Marie. I'm sorry. I almost didn't have anything, but I do have enough good stuff here to keep you going maybe longer than I should. And this is the HPLC of the same guys. And the last one off is considered the most greasy, and that's the diaryl sulfate. So those guys can be just hanging around. You could have 10 of them. You could think of making something like a peptoid with a bunch of sulfate linkages, and they're called inorganic, but I just don't buy that. I think the dumbest thing I've ever seen is these names before chemists. I don't want to have a name before my chemistry. I know I'm dumb in theory, but I know chemistry. I know the periodic table. I don't want to be a peptide chemist or a carbohydrate chemist. I don't see them. Why people? That's where our problem is. It's there. Inorganic, organic, what the hell are they talking about? There is no such thing. I'm sorry. That's the way it is. This guy is, in my head anyway, this is a sulfur. Oh, it's so beautiful up in the Andes. You see these big trucks coming down to make sulfuric acid. They throw it into the famous sulfur oxidizing system, make sulfuric, and then what do they got? Electricity coming from the dams, and everything's self-contained in Atacama to make copper. And sulfur is so beautiful in its orthorhombic form, but it has a million forms, and it's really amazing stuff. That's one thing you need. And the other thing you need, we don't have that much of. The Russians have, the Chinese have it a lot, and that's good for me because I go there a lot. And they every place I go, I've got a lab that has a 50-kilo bottle of Vicane. They get it in one day. How are we going to compete? Richard set me up with one. Well, Richard and I have a good friend, and he can move heaven and earth. He even has 3 boats down there by the famous what's it called, the Bund in Shanghai. These are so beautiful, but they're really low melting. They melt at 700. The oxide has got the same situation. It's got 2 minus spots, and you'd think, this one has got 2 fluorides, so they should have pretty comparable orienting abilities. Maybe fluoride, in principle, it could be better because it's easier to get the lattice or into a rutile structure. But this thing melts at 700, 3,300 degrees centigrade for the calcium oxide. That's why there ain't much fluoride in this earth. If there were, mountains might not be up there. And I wanted to say that water is special, but fluoride has got me going crazy. I need help. The thing is vicious in its own way, and it's like a bunch of piranhas with the little tails of 6 to 12 things. There's always an exposed free H, and it's worth more than water's free H, and it explains a lot that I didn't understand. So let's talk about fluoride a little, because it's more important to understand these basic things like electronegativity effects than it is to understand much else. Like structure is important. If you don't know it and you are able to know it, you'll look dumb. But structure is never very important because it's too much. There's too many kinds of compounds out there with structures. You need to find the ones that work. And the ones that nature uses are defined as working. That's all she cares about. Okay, what am I doing here? Okay, so the priorities of synthesis are to keep it short and simple, and to have if you had a perfect reaction, which we didn't till 2002, we got one, now we got another one, and there's one from Germany from 1905 that has been repopularized by Charlie, for his last name, he was at Southern Miss, and he died of a heart attack. A wonderful guy, and Hawker's carrying on the banner of this thiolene. It's a really tremendous reaction. The only thing that interferes with is phenols, which is kind of unfortunate when it comes to proteins, but it doesn't care about amino acids or anything. It adds to olefins. Well, what we got here is this idea of if you have a good reaction, you make a bond, you make it perfectly, you see whether it's anything interesting. If not, you try to use another perfect reaction, make another bond. And you do it 3 times, nothing happens, you don't keep going, you just throw everything away. There's nothing valuable in here, okay? It's a pain in the ass to keep track of compounds, and you don't really need to. You can make them without hesitation. You never need to know any spectra in this chemistry. I mean, it's important to have spectrometers, but you don't need it I've always been that way. I have to tell you, maybe it'll help you be better in chemistry if you're a student. I always knew what the reactions were from the starting materials. I knew what the products were about the end of undergraduate school. That was the game Tom Spencer taught me to play. I recommend it. If you look at spectra and then you get the product, that's ridiculous. What are you learning from that? That goes by, you can do it by computer maybe faster that way, but if you know, so you're learning reactivity when you lay those products down in some pecking order. And if you don't know what ytterbium does, then, well, there's general books on inorganic chemistry, mainly by the English school, that are awesome. They cared about inorganic chemistry. Well, here we go, calling it inorganic. But and yeah, here's MG's. He put 68 acetylenes or azides on things. So this reaction goes in blood. It goes anywhere, and you can just not stop the copper reaction. So it became a USB connector, and I'm really out of that area now. I use it to make these things in the screening for libraries, but I just can't follow it. It's out of control. It's got a life of its own. Finn's the guy who invented the bioconjugation, even though two other guys in our department almost published it first without asking him, who taught all of us how to do it. Sometimes things aren't good. And MG is a very generous person. He doesn't really care about that kind of thing. And, it's a really great thing that they have a way to grab stuff in fluids, gooey things, life, tissues, because it's hard to imagine why it could work, but it doesn't. We don't need to know that. We just need to know it works. That's what Richard would say. In fact, I love his famous one is, well, some guy asks you in biology, if you go out in the biology world and the guy's asleep, the famous one, another famous guy is talking, he's always going to ask you, when he wakes up, he's going to ask a question. And biologists will ask, what effect did the pH have? So, should I tell him? He said, well, I tried it with pH, tried it without pH. Didn't make any difference. Okay, that's the learner for you. Okay, now here's just to show you what it means to be reliable reaction. And that's what I get upset about when people say, we all know what good reactions are, click react. Well, we got lucky, so we got these special ones, and they don't have any competition yet. Those three I mentioned. So the idea that you have a good reaction, I agree. I loved it. 90% yield was more than enough for anybody over and over again, and even 80% was fine. But here's what MG and his student Chen Wang, who's really super full professor now in South Carolina. He'd probably go back to China in one of the famous slots there soon. But he put this on the virus particle, which MG is a great collaborator, and everybody benefited when Richard hired him because he collaborated with all the biologists. Jack Johnson's makes viruses by growing them on plants, and MG got really into that. So we had this 60 thiol attachment point on this, or MG did, and all we did was provide a ligand at one point that worked. That's the only reason Larry and I are on the paper. And so how do you know whether you got that number? Well, fortunately, dyes are extinction coefficients are big, and so you definitely, if they're far enough apart and don't have any interaction, you can get a really good number on the yield. It was 95% for 60 steps. And what that means, I don't have it written, but the Arithmetic Demon, that Bob Ireland, a great character who recently passed away, he wrote, in organic chemistry, we get too many asymmetric centers accumulating, and this is called the Arithmetic Demon, because if you don't get the right center, you get two compounds. So 60 steps now, I'm just making connections that aren't chiral, just connections to one. And if you go at 99.9 per step, you get the yield that's the yield that MG and Wang got. So that must have been at least the yield per step. It's that yield, 0.999 in brackets to the 60th power. And my wife was playing around a spreadsheet with our son-in-law, who's an engineer, and over in the plane coming over from California to our anniversary in Boston, and then she got this graph, which is good too. If you have 100% yield for each step, you go 100 steps. Well, of course, you got 100%. But if you have, I don't know if this is right. I didn't think it was that good. You have that kind of a yield, and you go 100 steps, you're still damn good. And here's 60. So it sort of doesn't quite bear out here, but look what kind of hit you take here at 90%. Where's that? There was 90, that one. It's ridiculous. People want to do something where they can guarantee they did what they said they did, connecting A to B, and they want to do it again. Well, they won't be able to. You can't separate things well. Polymer chemists have blocks that are huge, and they have one azide and one acetylene. They want to connect them, one block, polar to nonpolar, and they have the ultimate argument for need for fidelity of transformation, because it's like one group is in this room and the other one's up there in the balcony, and they got to find the ends of each other, and they got to find some coppers and all that kind of stuff to react. Okay, I think I'm getting where I need to be. This is the most stunning thing, nature. How she does it, she has top-down control, but how did she get the top-down control to put them together, take them apart, and get it all figured out and encoded in nucleic acids? It's just mind-boggling. But the things I worry about is we are big, blunt objects. We don't really control molecules. We use our hand for thalidomide victims. We use our feet. We can screw something on. We put a flask. We pour in Avogadro's number of this and that. We put a stir. We make atmosphere control. We put a catalyst in, real sexy catalyst. What do we think we're controlling there? We're smart. We know stuff by history of records of writing down, and it's amazing what we know indirectly, but it's all statistical mechanics. So my point is that if you can't make a guaranteed bond, then we don't have any control, really, of the kind that we need. And, it's all hoping and purifying. And so if you can make sure you made a bond, that's a dumb thing in some way. Nature wouldn't ever do that, because she needs to take things apart mostly in the important machinery. So she can't take those irreversible driven reactions. So she didn't teach us there were reactions like this. So that's one thing that's interesting. Okay, I'm almost done. I think to show the chemistry I wanted to talk about sulfates, you can catch in the publication. It's pretty well written. It's got 180-page full. It's a full paper. It's not a review. 180-page experimental. And this is the hero that got the sulfate chemistry working, and he went right in and did the polymer reaction this first week, and then he ended up to half a mole in the third week. And I'll show you what it looks like. You just put that stuff in with that and a little catalyst. We got a new catalyst now, which is invisible, but anyway, it doesn't take much catalyst. You heat them at 125 degrees, you melt them together, neat. They sit and look at each other for 3 hours, 4 hours. You add the catalyst, then out distills this quantitatively, and then you dissolve it in DMF and you shoot it into a methanol solution, and you get this polymer. And it's unlike this polymer, which is polycarbonate. I had this lens washed so it's clean of all its coatings. If I put this in a household ammonia overnight with a desiccator, say, we scientists would do the desiccator thing. You put the lid on, you've got something underneath it so you can collect the powder. You get powder out in the morning. It's urea and bisphenol A. And this polysulfate doesn't give off any bisphenol A, and it's stronger thermally. And so we're hoping that Richard's Institute, that he made famous, we can get somebody to pick this one up. It looks like China is interested. Dow was the guys who gave us the gas, but they don't speak to us for some reason. I don't know. Jane knows. No, it's hard not to talk. I don't ask questions and I don't answer questions. That's a problem. I don't know, but I try to get interested in your problems. And the only way I can get interested is if I know the structure. That's funny, isn't it? Because I only see potential function in that structure. For you, simple molecule. These molecules are going to be covalent most of the time. And they're amazingly subtle that way. And that's something I can't talk about much, but that'll be a good way to end it. Here I can just show you the evidence for the the wimpiness of sulfonyl chlorides. They are the least stable compounds that people have used. They're always going to crap in the bottle. When you ever make a tosylate, you got a lot of sulfonic acid in there. It's in the water layer. Nobody looks for it. So, the pyridine comes in, it reduces the chloride off. All kinds of things that people don't know. This one here, you just heat it up. It's the benzyl chloride in 30 seconds, and then it goes black. And this one is still around a year from now if you heat it for that. It just doesn't do anything. We have some of these that are 50 years old, through the desert of America twice on the way to Stanford, and back 3 times, actually, and then back to California to Richard's place. And Richard, by the way, paid for all this chemistry, and with Sam Skaggs mainly. There was no grants here. I can't get grants for click chemistry. It's too simple. They don't like simple. They want polytoxin. And that's what this is my idea of a reactor. That guy is, see, this is a German back in 1908. This is how they made one of the key elements for dyes. I don't know where they make it now. They don't even teach aromatic chemistry while in school anymore. It's all going off to proteomics and God knows what. This is the really great way to make pieces. It's the first click chemistry. Just heat. You make phenol from this. How do you get a phenol from a sulfonate? There's this fantastic reason. I think I know the mechanism, but nobody cares anymore because all that chemistry went away and the Germans were shut down for 4 or 5 years, and the dye industry didn't lead to the medchem. Medchem should have been dye chemistry continued, and that's about it. You'll see that this is all about what doesn't happen with sulfur. It gets reduced. Phosphorus doesn't ever get reduced. And where's my, here's the one I think people would like. If you've ever refluxed something, aniline is not innocent, If it's splashed on, it's dry, obviously, at 184. You put in 5 mils of this. We did this to check the old German literature, and you blank, and no reaction after 4 hours. You cool it down, you add a dollop of water, you stir it, it's over in a couple hours. There's something interesting going on here. And it was phosphorus. I didn't get to my table. Where's my periodic table? I got to show it. Okay, there it is. Okay, Stairway to Surprises. Actually, it's the stairway to heaven. Look at this. Each time, that's the last stop in the universe, right there. And if you get there, look at this. Unbelievable properties. This is the chalcogens and the halogens. Wham! 100 and how many degrees? 60 degrees, and then here with one little wiggly hydrogen bond. You can only have 2 things, and it's still way up there. And then if I take the next one, the ammonia, the pycnogens, well, they just go like that. And if I take the carbon, they just go like that. There's a lot of stuff we don't understand about that. And also that's all. Thanks. Okay.
What a wonderful talk. So interesting and at the same time so entertaining. We are a little bit behind schedule, but I do think there is room for 1 or 2 questions. No, we take it. We please.
I need hearing aids. I got to go to Costco when I get what?
How does the water influence the reaction? Why does it play such an important role?
Yeah, well,
How does water?
I think I sent you I sent Jack Dunitz about 8 years ago about the slides from Rudy Marcus's work. It comes from Peter. Where's Andy? Yeah, Peter. What's his name? And yeah, 2 physical chemists at Houston, and they had that was the first paper, 89 or 86 or anyway. That was the first people who talked about the protons would be dangling at the interface because water's in pain. It's trying to get it has a high surface tension. It's trying to get as much as it can in its bulk, and it has that left over, and they're not hydrogen bonded, and they're normal to the surface. And Rudy thinks there are 35 per 30 square angstroms, and that's the electric field that Geraldine Richmond describes. But then I hear Chandler, and he doesn't say anything like that. He talks about evaporated water. So I'm not at all happy about the way the world's working in the important areas. These guys don't talk to each other, George, and you talk to, you know that too, don't you? What is it, like ships passing in the night here on an important issue? But no, the water, it adds up. And if I showed you the transitions, it's like the ground state. It's a Ene reaction. So it's got, and by the way, this is what these wherever water is at an interface, as long as it's liquid. See, you got to pay for this. This is the second law here. You got to keep it liquid, or we're really screwed. I mean, but you wrap these things up in 3 dimensions, and you put some backbones in them. It looks a lot like a proton, because wherever you got a plus dipole, you got a minus too, right? And I don't know. I just think water is a wimp at hydrogen bonding. HF doesn't have a bulk thing that it's worth a damn, right? Ocean slabs are miles deep. But HF, once it gets a hold of a weak spot, it's like piranhas. They come in and they just go crazy. That's what I think. I don't know.